Section 1.5, Rotational Kinematics. In one-dimensional kinematics, we dealt with movement along a straight line that we often called the x-axis or the position axis. We could have a point here, P, and it could move to point P prime through some displacement over a course of time. From this, we could derive all of our quantities, including acceleration, velocity, and average velocity. In rotational mechanics, instead of dealing with a straight line, we want to deal with a circle. In this case, for uniform circular motion and for rotational mechanics, we will be dealing with a fixed radius of r, which we can set for equal to 1 for ease of use. That means that the only thing differentiating this point here from this point here is its angular distance that we call theta. Theta is the rotational equivalent of position because our distance along this line is defined as being a different angle away from the origin, which is this point here where we started. So we can now derive all of the different quantities that we looked at back in one-dimensional mechanics. We'll start by looking at average angular velocity. We call average angular velocity omega bar, and this is equal to the change in theta over the change in time. This is in units of radians per second. Likewise, we can do a limit and find the instantaneous angular velocity. Omega of t is equal to theta dot of t. And this is in units of radians per second as well. We can define average angular acceleration as delta omega over delta t, which is in units of radians per second squared. Finally, we can define instantaneous angular acceleration, alpha of t, as being equal to theta double dot of t, or omega dot of t, which is equal in units to radians per second squared as well. Thus, similar to that of translational kinematics, we can go between acceleration, velocity, and position by integrating, and the reverse by differentiating using calculus methods. Sometimes there are other magnitudes that we like to use, which we will define now. We will define the frequency as being omega over 2 pi. This is in units of 1 over seconds, which is equal to hertz. We will also define the period, t, as being the inverse or the reciprocal of the frequency. This is in units of seconds. Now we shall take a look at our equations of motion. We shall do this by integrating uniform circular motion, a constant alpha. Alpha is equal to omega dot of t. Thus, we can say that omega of t is equal to omega naught plus the integral between t naught and t of alpha dt. Thus, we can define omega additionally as being theta dot of t, thus allowing us to define theta of t as being equal to theta naught plus the integral between t naught and t of omega dt, which is equal to theta dot plus omega times t minus t0 plus the integral between t naught and t, again the integral between t naught and t, of alpha dt dt. If alpha is constant, we will have uniform circular motion, and we will arrive at the following kinematic equations. We will get that omega of t is equal to omega naught plus alpha times t minus t naught. We've seen this many times before. We also have theta of t equals theta naught plus omega naught times t minus t naught plus 1/2 alpha t minus t naught squared. Again, if we say that alpha is equal to 0, then we will have uniform circular motion such that omega is equal to omega naught and theta of t is equal to theta naught plus omega naught times t minus t naught. So uniform circular motion, alpha is equal to 0, omega of t is equal to omega naught, and we also have that theta of t is equal to theta naught plus omega naught of t minus t naught. Now it's all well and good to have these equations of motion for rotational mechanics, but it doesn't really mean much if we can't connect this to linear motion. So let's now connect this to linear motion. We are going to start with a circle with a position vector r from the center O. So let's draw this out. So we've got a circle, and from the center, we are going to be a position vector r away from the center O. And the edge we will call point P. So we could use e sub x and e sub y basis vectors, but we would rather switch to a polar system. So the system that we would like to use is the polar coordinate system, which means that the vector for the radius, we will have an e sub r vector, which will be always sticking out from the circle normally. And then we will have a tangential theta hat, e sub theta vector, basis vector, which will always point perpendicular to the radius and the basis vector in the direction of motion. So now we will need to write these basis vectors in terms of our little other vectors. So we could have a case where I have e sub theta like this, and I could have e sub r like this. And we will need to use an xy basis vector in order to decompose this. Now this is going to be translated rotated by an angle theta away from e sub x and e sub y in the vertical. So we can define this components-wise and get a nice definition for our basis vectors, because our basis vectors are going to change. That's something that's important. So if we find our velocity, then we're going to need to be taking the derivatives of the basis vectors as well, which is something that's a bit trickier. So let's actually define what our basis vectors are going to be components-wise. Let's define e sub r. So e sub r is going to be equal to, so its x component is going to be the cosine of theta times e hat sub x plus the sine of theta e hat sub y. Okay, now let's find the magnitude of e sub r. E sub r is going to be, it's very easy, it's going to be the cosine squared of theta plus the sine squared of theta, which is equal to 1. Okay, now let's find the expression for our e sub theta vector. So to find our e sub theta vector, we need to look once again at the basis vectors, and then we can find that our e sub theta vector is going to be equal to our x component is going to be the negative sine of theta. So we have e sub theta is equal to negative sine of theta times the x basis vector plus cosine of theta e sub y. Okay, now we need to find the derivatives of these basis vectors. So we are going to differentiate with respect to theta. So first, we will differentiate e sub r with respect to theta. So we have cosine theta plus sine theta. The x and y basis vectors are going to be held constant, so don't worry about that. So if I have cosine of theta, then I'm going to go to negative sine of theta. So we get negative sine of theta, e sub x, and then the sine goes to cosine. So we get plus cosine of theta, e hat sub y. Well, what does this look like? This looks just like e sub theta. So we set this equal to e sub theta. That's interesting. Now let's find the derivative of e sub theta by d theta. And we are going to get negative cosine of theta e sub x hat minus the sine of theta e sub y hat. And this is equal to the negative e sub r. Okay, so now we've differentiated all of our basis vectors, which is wonderful. But now what we want to do is we want to start finding the relationship between these rotational equations and our translational equations. So, first of all, let's determine our position vector to start. So the position vector, r, is going to be equal to, it's going to be equal to x component and y component. Well, so let's see what we've got. We don't really have a y component, but we have an x component, so we're going to be at a radius, r, of the circle, and 0, which is equal to r e hat sub r. Okay, so now we need to differentiate this. So in order to find velocity as a function of time, we need to take the derivative of the position function, which is equal to the derivative with respect to time of r e sub r. Okay, so how do we deal with this? So we can pull out r because that's a constant, so we get r d by dt e sub r. So we only really know right now how to take the derivative with respect to theta. So what we're going to do is we're going to use the chain rule. We're going to use theta as an intermediate variable. So v of t is now going to be equal to r, derivative of e sub r with respect to theta, and derivative of theta with respect to time. Now this is going to be equal to r times omega times e sub theta. Now how did I get that? Well, this derivative, d theta dt, that's defined as the angular velocity, which is omega. Now this here we already found earlier. We found that up here. That was e sub theta. So we get that the velocity function is equal to r omega times e sub theta. Okay, so now we have an expression for our velocity, but now we'd like to find an expression for our acceleration. So the acceleration, a of t, is going to be equal to the derivative of velocity. Now, what are we going to do here? So what we're going to do is we are going to take the derivative, we're going to take d by dt of r omega e sub theta hat. Okay, now unfortunately we're going to need to take the derivative of everything here, which means that we need to apply the product rule. Now if you remember the product rule, it says that if I have two functions, f, g, I want to take the derivative of that, then I need to do f prime g plus g prime f. And we can continue, and you see here we actually have three things we want to take the derivative of. So we are going to need to go through all of those permutations. So we are going to get dr by dt omega e sub theta plus r d omega dt e sub theta plus r omega d e sub theta dt. Now, two of these are trivial. The next one is not. So what are we going to get? So here we simply get, we will get r d omega, because this is 0, r is a constant, so we get 0 there. So we get r times alpha e sub theta, and that should make sense because here we're taking the derivative of omega with respect to time, and that is angular acceleration. And then plus r omega, and we need to use the chain rule again, d e sub theta, d theta, d theta dt, which is equal to r alpha e sub theta plus r omega. D sub theta by d theta is going to be negative e sub r times omega again, because we're differentiating there. So you can write this more compactly. So the acceleration is going to be equal to r alpha e sub theta plus r omega squared, or minus r omega squared e hat sub r. Okay, so there we have our acceleration. And it's important to note that we also have something called the centripetal acceleration. So if I define the centripetal acceleration, a sub c is equal to r omega squared, which is equal to v squared over r. Okay? All right. So why don't we now try an example? So let's say that I have at some time t equals 0, I will start at an initial angular velocity of 0, and then at some t equals t, I will have some angular velocity of omega equals n revolutions per minute. Okay, so then we're going to wait for the rotation to stop. So at t equals t prime, then we are going to have omega equal to 0 again. So what is the linear speed at the edge of the rotor at t equals t? So the velocity, we're really looking for velocity. Velocity is going to, I'll put a little example thing up here so we know we're doing an example. V equals r times omega, right? And we have r, which is the radius, times 2 pi n over 60. Right, so where are we getting that? So we're going to n RPM. So omega, to find omega, we need to go from frequency, because we have n RPM here. We need to multiply by 2 pi, and then we need to divide by 60 as well, because we are dealing with an amount of minutes as opposed to seconds. So we will get 2 pi n over 60 times r, which is equal to r n pi over 30. And this can be in, let's say this is in meters per second. Okay, so then I also want to find the average angular acceleration between t equals 0 and t equals t. So alpha bar between 0, and t is going to be equal to the change in omega over the change in time, which is equal to n pi over 30 times t. Okay, so that, and then meters per second, radians per second. Okay, so that is the rotational kinematics examples. Thanks for watching.